Hi there, Augie Kennedy here with Super Awesome Calculus, and we're still on Chapter 2, Taking It to the Limit. So lame. And today we're going to go over Section 2.3, which is all about finding limits using the limit laws. Last time we talked about what a limit was and how you could find the limit of a function. We did some direct substitution, we looked at various limits. Now we're going to find other ways to get limits. So first, let's go over the big problem from last time. Now the problem was determine the infinite limit as the limit as x approaches 3 from the right of the natural log of the quantity x squared minus 9. Now the best way to do this, the easiest way, is to know something about transformations that we talked about last chapter. We know that our function is ln x squared minus 9. Well, what we know is that the natural logarithm function looks like this. It crosses over here at 1, 0. That's the natural logarithm. And we know that at 0, there is a vertical asymptote. Okay? Now, as I mentioned in the last lecture, that vertical asymptote, that means that the smaller, this is a great example of a limit, the closer you make the natural logarithm to 0. Like if you do 0.5, you're going to get a small or a large negative number. If you use a very small positive number like 0.1, you're going to get a much larger negative number. And if you go all the way down to 0.00, as arbitrarily close to 0 as you want, you're going to get an arbitrarily huge negative number. And what that means is that the limit as x approaches 0 from the right, coming this way, of ln x is negative infinity. And as you might expect, if you look here, we look at this function, the ln x squared minus 9. Well, we're looking for the limit of this function as x approaches 3 from the right. So let's try direct substitution. That would be the natural log of 0. That's not very good. We can't use that. But think about why? Think about what happens when the natural logarithm is 0 in a regular logarithm function. We get a vertical asymptote and the limit is negative infinity. As you might guess, the exact same thing happens here. It's just simply a transformation of sorts, and you're going to get the same vertical asymptotic behavior, and the limit and the answer to the big problem is negative infinity. There you go. And remember, a limit at negative infinity means that it doesn't exist because there's no concrete number that can be assigned to that limit. Just remember that. It's very important for later. All right. Now today, we're going to talk about the limit laws. And the best way to talk about the limit laws is to just go over them. I mean, the book does a really good job explaining these limit laws. So let's look at some of them. Let's assume that we have two things. We have c is a constant. Oftentimes you'll see in this course especially that we use c because the numbers, the random numbers are generally not as important as the formulas. So c could be 9, c could be 7, c could be anything you want. And if it makes you feel better on exercises, go ahead and make c equal 5 or something simple to work with, if it helps you. And we want to assume that limit as x approaches a of f of x and limit as x approaches a of g of x both exist. We want to make sure that they both exist. All right, now, what that means is that the first law is that the limit as x approaches a of f of x plus g of x is equal to the limit as x approaches a f of x plus the limit x approaches a g of x. In other words, the limit of a sum is the sum of the limits. Very easy. We can do the exact same thing here too by putting a negative sign there. The difference, or the limit of a difference, is the difference of the limits. Very simple. Also, here's number 3. Limit as x approaches a of some constant times f of x is equal to that constant times the limit x approaches a f of x. In other words, if you've got a function, you can just take, and the number in front of it, you can just take the number outside and then work with the limit on its own. We'll do that plenty of times in this course. So 3 is definitely something to remember. Also, we're gonna change number 2 now to number 4. Let's make it the product of the limits fx, gx. Well, the limit of a product is the product of the limits. Very, very easy to understand. And number 5, you knew that this was probably going to happen. Limit as x approaches a of f of x, the rational function, over g of x equals the limit as x approaches a of f of x over limit as x approaches a g of x, providing that the limit as x approaches a g of x does not equal 0, because remember, we can't divide by 0. So the sum of a limit, or the limit of a sum is the sum of the limits. The limit of a difference is the differences of the limits. The limit of a product is the product of the limits. You can take a constant outside and multiply that constant times the limit. And the limit of a quotient is the quotient of the limits, providing that the limit of the denominator does not equal 0. So those are some limit laws. They're pretty good. Now there are also some little kind of one-off laws that we're going to go over really quickly. We're going to look at a couple examples of these, don't worry. But there's still a few things that I just want to go over. This is a hell of a board. Okay. Generally speaking, using that product law, we can find that the limit as x approaches a of f of x to the nth power equals the limit x of a f of x to the nth power. In other words, if we want to figure out the limit of a certain function to the nth, we can just figure out the limit and take that to the nth power. That's useful too. This one is very, very obvious. Here's another law. Limit as x approaches a of c equals c. That's like saying the limit as x approaches 2 of 3, it's going to be 3. Very, very simple. And also, the other thing that kind of goes hand in hand with that is the limit as x approaches a of x is a. That's the line, y equals x. You can graph these and you can figure out why those two rules work if you choose. Also, the limit as x approaches a, I know that this is like just a lot of mechanical work, but trust me, it's going to be useful later. X to the n equals a to the n. That's basically saying that polynomials are going to basically work this way. This is just the way that they're going to work. Also, you're going to see limit as x approaches a. This is all very intuitive, I'm sure, of the nth root of x equals nth root of a, assuming that n is, if n is even, that a is greater than 0. In other words, it's going to be gross. And you're going to deal with imaginary numbers. So, okay. And finally, there's something that we already did last time, and that's direct substitution. And that's the way that polynomials work. If f is a polynomial, and a is in the domain, then the limit as x approaches a of f of x equals f of a. Now what that means is that if we have a function like this, if 2, x equals 2, and 2 is here, 2 is in the domain, and it's defined, well, then the limit is going to be exactly what it is. It's going to be 2, or whatever that output is. It's going to be f of a. So the limit as x approaches 2 of x squared is 2 squared. It's 4. Very simple. The limit of, and using some of those limit laws, we can say, okay, the limit as x approaches 3 of x squared minus 2x, we can look at that and we can realize that that's saying the difference of the limits can go, that's the limit as x approaches 3 of x squared minus the limit as x approaches 3 of 2x. 3 squared is 9, minus 3 times 2 is 6. The answer is 3. So that's the limit laws in practice, or a couple of the limit laws in practice. There's something very important to talk about here. And that is the Squeeze Theorem. We're going to use the Squeeze Theorem an awful lot throughout calculus. And you're going to see it, it seems really obvious when you see it. You're going to be like, well, this, duh. But trust me on this. Okay, the Squeeze Theorem states that if we have 3 functions, f of x, which is less than or equal to g of x, which is less than or equal to h of x. I'm going to draw this so it's going to make some sense. Where x is near a, except maybe at a. Remember, this is calculus. We're talking about things that are near something, not necessarily what they are, but what they're close to. And the limit as x approaches a of f of x is equal to the limit as x approaches a of h of x. If these two limits are equal, if that limit and that limit are equal and g is in between them, then the limit as x approaches a of g of x is the same. That is the Squeeze Theorem. Now the Squeeze Theorem is probably easiest to see in a graph. It's very, very easy to see in a graph. Let's look at it. Let's just draw a little coordinate plane here. Alright, here's going to be h of x. And here is f of x. And there is g of x. Okay? So as you can see here, we've got 3 functions. And here is the point A. Now let's look at the way these functions are behaving. f of x is less than h of x, but they both look like they're going towards the same limit. Let's call it q. If that's the case, if the limit as f of x approaches a is q, and h of x looks like it's heading to q, and g of x is in between them, well then obviously at point A, g of x is going to q. And that's what the squeeze theorem looks like. Okay. Now, let's calculate a couple limits in the few minutes that we have left. There are a couple limits that I really want to look at, because there's some tricks that I think everybody should know. The first is very important, and I actually remember this trick because I had the hardest time with it when I took calculus in school, at college. Basically, here's an example of something that's kind of tricky. I have an example. We're going to find the limit as, and I'll call it x approaches 0 of x squared plus 9 over x squared, and then put a negative 3 up in the numerator. Okay? Now the first thing we do is we try direct substitution. We can't do that though because that would make x equal 0, so we're going to have to try something else. The problem is that we have a radical in the numerator. We don't want that. When we're figuring out limits, we have to do something called rationalizing the numerator, which isn't exactly the easiest thing in the world, but it's not so bad. All we need to do is we need to get rid of the radical in the numerator. And the best way, and the way to do that, is to multiply both sides by the same thing. Remember, in algebra, you can multiply the numerator and the denominator by the same thing. It's essentially multiplying by 1. So, here's a creative way of writing 1. T squared, or x squared, they use t in the book, x squared plus 9 plus 3 over x squared plus 9 plus 3. So you see we have the square root of x squared plus 9 plus 3 over the square root of x squared plus 9 plus 3 outside of the radical. That's technically 1. And when you multiply that together, what we're now looking for is the limit as x approaches 0 of a new numerator. In x squared plus 9 minus 9 over x squared times the square root of x squared plus 9 plus 3. And we can see that that's not even as reduced as we can make it. That x squared plus 9 minus 9 will cancel out, and we'll get the limit of x squared over x squared times square root of x squared plus 9 minus 3. And now what we do, we're almost ready to solve this, but we still have an x squared down there. If we try direct substitution again, we're going to fail, because we're going to get 0 up top, that's fine, but we also get 0 in the denominator because x squared is 0 times that whole quantity. No good. So we have to get rid of that x squared in the denominator. How are we going to do that? Well, we're going to divide by a common factor. Now here we have the common factor x squared. Okay? So let's divide the numerator and the denominator by x squared. And if we do that, here's what we get. We get 1 over x squared plus 9 square root minus 3. Now we can do something here, because now we remember the quotient law of limits. The limit of a quotient is the quotient of the limits. Limit as x approaches 0 of 1 is going to be 1 over the limit as x approaches 0 of x squared plus 9 minus the limit as x approaches 0 of 3. And what do we get here? Well, we can also move this radical under here. What do we get? We get 1 over square root of 3, because x squared at 0 is 0, plus 9 is 9, and the square root of 9 is 3. Oh, I forgot a plus. This is supposed to be plus, because you remember we had plus 3. Arithmetic error, I apologize. Plus the limit of that. The limit as x approaches 0 of 3 is 3. So the limit is 1/6. And there you have it. We went over several different laws of limits in this exercise. You can see we rationalized the numerator, and then we divided by a common factor, the numerator and the denominator. Then we used the limit laws. The limit of a constant is the constant. That's why limit of 1 is 1. Then we used we broke down the x squared plus 9, the square root of that. We put the square root of the limit of that quantity. And we created a sum here. So we have the limit of 2 sums. And if you can follow all of that, you'll be in very, very good shape for limits. Now, today's big problem is going to require you to evaluate a limit. Today's limit is the limit as x approaches 7 of the square root of x plus 2 minus 3 all over x minus 7. You're going to want to use some of the techniques that we talked about in this lecture to solve that. And if you do, if you use them, you should be in good shape. Well, until next time, I'm Augie Kennedy, and take care, y'all.